Day 3, we'll look at how you can read a graph, and we'll learn about something called function notation. So in class, we'll do this investigation. How long will it take to stop? If you've ever been in a car, when the driver slams on the brakes, you know that the car does not come to a stop immediately. Braking distance refers to the distance a vehicle will travel from the point when its brakes are fully applied to when it comes to a complete stop. Number 1, what factors do you think will affect a car's braking distance? So one thing I can think about is maybe the weather. If it's rainy out or icy or snowy out versus if it's a nice day, that could affect your braking distance. Maybe the condition of the road. Condition of your brakes. Also the speed that you're traveling at. The graph shows the relationship between a car's speed and its braking distance. Some values are also given in the table below. So both of these are the same data, just different representations. A, what is the braking distance of a car driving 60 miles per hour? So if we look at the table, we can see that when the car travels 60 miles per hour, there is a braking distance of 171 feet. B, what is the braking distance of a car traveling 40 miles per hour? And how do you know? Well, it's not in the table, so we can take a look at the graph. We can start when the speed is 40, go up and over. We got to see, what is this going up by? So if you notice, 1, 2, 3, 4, there's a gap of 4 to get to 50. So we take 50 divided by 4, we can see what it's going up by every time. And it looks like, let's make this thinner here. It goes up by 12.5 every dot here. So this would be 50 plus 12.5 plus 12.5. Okay, so that's 25. So this would be 75 right here. So 75 miles per hour. It says the ordered pair 73, 254 is on the graph. What does this mean? Well, remember in an ordered pair, X comes first and Y comes second. And we talked about independent, dependent variables, how the X is the independent variable, which in a graph is on the bottom of the graph. In a table is at the top of the table. So this would be speed. So when the speed is 73 miles per hour, the distance, the Y value, or what's on the Y-axis, it would take 254 feet to come to a stop. A car took 200 feet to come to a full stop. Can you estimate the speed at which the car was traveling before the brakes are applied? So now we have the speed, which is the Y value. It's not in the table, but we can look at the graph. We can find 200, go over and down. And let's see what this is going up by. So it's 1, 2, 3, 4, 20 divided by 4 is 5. So it looks like each of these are 5. So this would be, although this, I don't know if the 80 is in the right spot. Maybe the 80 is over here. So this would be, looks like 65 miles per hour. So if you're traveling at 65 miles per hour, it would take you 200 feet to stop. Now it says find f of 80 and interpret the meaning of this value in the context. All right, so f of 80, this is actually going to be our x value. This is in the form f of x. All right, so f of 80 means when the speed is 80, how long does it take to come to a complete stop? Okay, and we can take a look when the speed is 80, 305 feet. So we can say f of 80 equals 305 feet. And it says use function notation. So this is called function notation to express a car that's traveling at 45 miles per hour. This is the x value. So when it's 45 miles per hour, it will require 96 feet to stop. So in function notation, we put the x, or the independent variable, in the parentheses, and the output is here. So this is the input. Here's the output. So when the input or speed is 45, the output or braking distance would be 96 feet. So this is function notation. It tells you what the input is, and then it wants you to get the output, or it might give you the output and you can find the input. So it says in general, it's this form. F of x is how we say this. This is the name of the function f, and then x is the input, and then the whole thing is the output. So f of x is how it's said. You can use other letters if the name of the function is different, like g of x, y of x. Well, we don't usually use that. M of x, n of x. Okay, so let's check for understanding. So again, a function notation is a concise way to refer to a function and describe its input and output. So it says a graph y equals f of x is shown. So the name of this is f of x, which is y. Find f of -2. So it's saying in this function, if the input, or x value, is -2, can you find the output? So the input's -2, we're going to go up and over, and we would say that the output is 2. Find f of 1. Okay, so when the input is 1, find the output, which is 3. So we would say f of 1 equals 3. Now it says f of a equals 6, find the value of a. This time it gives you the output. It wants you to find a, which is the input. So if we have the output, this time we're going to go here. Output is 6, go over and down, and the output is 5. Or sorry, the input is 5. So we would say f of 5, when the input's 5, the output is 6. There's the answer. Okay, let's try a few more. It says, let n of t represent the number of people in line at a barbecue food truck, t hours after the food truck opens. Interpret each of the following statements in context. Okay, so this is hours. The input is hours, and the output is the number of people. Okay, so this is saying after 1 hour, there are 11 people in line. This is saying the number of people in line after 4 hours is more. So here's greater than the number of people in line after 6 hours. This is saying the number of people in line at when they open is equal to the number of people in line after 3 hours. And this is saying after our hours, let's switch colors here. There's 34 people in line. Okay, last check for understanding question. Physicists have discovered that there's a pattern or rule that can determine the braking distance based on a car's speed. Take the car's speed, square it, and divide the result by 21. Okay, so we can say, let's call this speed S. S, braking distance. Okay, so speed of X equals the distance. Okay, so to find the speed after a certain amount of time, take the car's speed. Oh, actually, it's braking distance. I'm going to change the variables. Okay. So I'll call it B for braking distance. And we'll say X is the speed. All right, so take the car's speed, square it, and divide it by 21. So here's our function. The braking speed when the car is going X miles per hour is the speed squared divided by 21. Oh, it wants f of s. Okay, so we can change it. All right, so f of s equals the speed squared divided by 21. So the goal today is, can you read a graph? Can you interpret something that's in function notation or put it in function notation? So your assignment will be the next page, so just page 10, and we'll go over any questions in class.